In the last session, we covered like exploit development basics. I don't know how many of you guys were there at that time, but it's like some of the material is dependent on these things. And for completion, I will like slightly go through the recap, but I will not cover the entire thing. So you have to follow. If you want to understand it clearly, then you have to follow the previous presentation. And we have all the presentation and all material is on our website, securityexploited.com. So you can go there and you can download the presentation and the reference links and material related. So, I don't know, like in the discussion session, they were saying thin line into the legal and illegal. And there is a, like in security from my point of view, I do not define these things because there is a cyber warfare going into one country and another country, right? You cannot define these things in security. This is the biggest, the thing in that. But we have a disclaimer, here is a proper disclaimer that we are not doing it. And this is the acknowledgement section. We are like null and garage operators. And of course the Thorpos guys, they arrange the menu. So this is a little bit about me, and I'm a security researcher. I'm working for McAfee Labs, and this is, I think, the thing that I have just changed from the previous thing. So the thing is that, as I mentioned, that the material that today I will take is not up to that advanced that I'm saying that I'm showing you something that is very dangerous. I'm keeping the actual all the things into this. This is covering the stuff that I will cover is covering everything, but keeping it simple as possible from my point of view. So I will be using a little bit of zigzag approach. I'm not following the all just start to end things, but I'm jumping between some hard topics and some low topics in between. So the thing that I cover in the beginning is the recap, and then I will talk about the stack-based protections that we have implemented by the operating system. Then I will cover the client-side exploit, that is a very big part, and the technique heap spray notably into that. And then I will move on to the more advanced protection that are a little bit difficult, like DEP and DSLR. And then if time permits, then I will take about 3 4 minutes. So in the recap, so if you mention, then last time I created this type of diagram in which I said that this is our EBP and this is our red address. This is a stack, and somewhere down here is our pointer to next stack, and this is our stack, and this is the stack. Now the stack grows in this way, and the overflow comes in this way. So what does it mean? It means that we have the higher address here and lower address here, because stack grows downward, and from the higher memory address to the lower memory address. So I just changed these things. In the memory, these things is just reversed. But when you see in the debugger or any kind of tool like PolyDB, you see exactly this kind of snapshot. You have higher address there and the lower address is there. So when a function call, actually before the call, it do the call statement actually put the return address of the next address of the instruction on the stack, and then it land into the actual function. That actual function share the EBP of the parent function, or this parent and child is my notation just to clarify these things. Actually it is a caller and callee relationship. So the caller, the callee actually put the EBP of the caller, so that the EBP is basically EBP register is used to track the variables of the local variables of the function. So that when the callee return to the caller, it will get the EBP same and it can reference its local variable accordingly, right? So this was the case. And in the EIPO, right, I mentioned that we overflow, we start from here somewhere where the function is taking the vulnerable, calling the vulnerable function, and we are overflowing this data. So it's going through this and we hit this position. We hit this position. When the function return, we manipulate this position and we jump into our payload. That is like jump PSP, because our payload is going to be there. So we'll just at this location using a jump PSP instruction or something like that. In the SAV, right, I mentioned that instead of going in this way, I just overflow this thing the way along here, and I will overwrite these two things. I will overwrite this SAV with a pop-up red Or I also showed like in the why we need pop-up-ret instruction. Or instead of the pop-up-ret, we can use the similar kind of instruction, but pop-up-ret is like the simpler form of this thing. So we overwrite this with that type of address, and then we land into the pointer to the next step. And after that, we take a short jump to land here or backward. I will discuss a bit more about it in later slides. So this is a classical recap, I would say. Now the question is that which one is reliable? When we have the both, when we have the EIP override and we have the say override, then which one we consider is it's supposed to like work better, or it's like my personal decision. I want to take this type of. I want to go with the EIP override or with the say override. So this is the question right now here, and this question is very crucial and important. Actually, you may not realize the importance here, but in the later section I will say that, and I will cover this question later and probably with the answer as well. So these are the actually protection enforced by the OS and the operating system. So I am saying that OS and operating system because it is the combination of both. When you say operating system and the processor, and then the processor and operating system work closely with each other, and they enforce some of these protections. Some of are like completely dependent on the operating system, while some of these are dependent on the processor as well at the hardware level. And this diagram is basically covering the most notable things in the or this term may be coined by the Microsoft or maybe some other researcher, but these are the names that are actually onto the documents. And there are some protection as well that are not into the documents, but they were implemented by the operating system, or more specifically I will talk about the Microsoft vendor. So this is the ASLR. ASLR is the bigger one because it is the bigger one. I will just talk about a bit later. And DEP is the data execution prevention, and this SEOP is basically exception handler override protection. So, and GS cookies and SafeSet and forced ASLR. Forced ASLR is not like committed by the Microsoft right now, but it was posed by from Microsoft officials. They said that it is coming into Internet Explorer 10. I don't know if they released the Internet Explorer 10, or maybe they are like doing with Windows 8. This upgrade, something like that. But this forced ASLR, I will discuss a little bit about the forced ASLR, but it does not exist right now. It is coming. We are not saying that it currently exists. And there are something that I marked here, like safe unlinking and heap cookies, that are specific to the heap, like heap header encryption or something like. So these are not as named as these things. So I just mentioned for the completeness that these things also exist into the protection mechanism. Now, we know that here we have the EIP override and the SAE override. Right? We previously exploited these things. In the previous session, we explained how you can easily manipulate and how you can easily get the control of the entire system. But because these things are very crucial, you are taking the you are taking the advantage of some other computer, or you are compromising the integrity of the other computer. So the operating system, or maybe the entire community or the authority take preventive measures for these things. And those were like, when you override the EIP, then you have the GS cookie. I will talk a little bit like what the GS cookie is and how it works. And when you do the SAE override, you have two protection mechanisms. One is this safe SAE, which is a way longer, and one is this SAE, which is introduced in the Windows, I think 7 onward or Vista onward, something like that. So, but the interesting thing about these protection is that they are the compiler option or the linker option, you can say. So, when you are writing your code, you have to compile with these switches, GS and the safe SAE. If you do not compile, then it doesn't work. So this is the important thing here, because it is a compiler and linker option. So it is the total responsibility of the programmer that he should know these things and that they exist. Now the GS cookie. Now if you remember, we overwrite this location, we overwrite the EBP, and we overwrite the ret here, right? So in the GS cookie, what they are saying is that, okay, if we are doing this thing, then what we do, we put a value here, 32-bit random value, a complete random value that is not guessable. this is like a random 32-bit because it's a 32-bit architecture I am talking about. So say it's a 32-bit. So, and when you return from the function, you match this value because you overwrite this thing. So you have to overwrite this thing, and this thing. And when function return, it will check this thing. And if this check fails, then either it will call a security exception. What is known as security exception is just used to log some information just for the programmer point of view, where which function actually caused this problem or something. But most of the time it doesn't. Programmer does not include this exception. And if the exception is not there, then it's finally go terminate. So actually, it is blocking our exploit because if the application is dying, the application is not executing our code, and it's just simply terminating. So this is actually the code that actually put the cookie. So the security cookie, as you can see in this here, that we are bypassing, we are passing this information into the EAX register. This security cookie is generated by init security cookie function inside the program itself. When you compile, the compiler adds this thing, and it's completely random. And if you see the function prologue, this is the function prologue. It builds this stack frame for this function. So you see that it is passed into EAX and then XORed with the EBP register, right? So, and then it's again passed into the EBP plus var4. Here the var4 is this is the IDA notation. So var4 is basically -4. So if you need anything EBP -4, it means you are going there. So if you are going there, it means you are going into the color area, not the color area. If you are here, then you can say it's an argument. Then you use EBP plus. If you are getting minus, it means you are going down, and it is the stack goes down, right? So it is the area of this right here. If you name EBP, this is the EBP. Let's say because we on the above instruction we use move EBP ESP, which means the EBP is also currently point at this location, and we are using -4. It means it's directly here. So when we overwrite this thing, then we have to overwrite this thing as well. And in the function and if you look, then before like blindly returning into the things, that as well in the previous case that we were returning to the blindly on these things, now it is calling a security check cookie. And if you remember, if you look into this, then it's moving the EBP var4, which was like inserted here into the ECX, and then XORing the ECX with EBP, it means it's returning the true value of that was XORed previously, and then calling the security check. And if you check the security check function, then it's comparing the ECX value with the security cookie. And if both things are not same, then it will report to the JS failure, which is the function that is used to terminate the application. Right? So yeah.
Amit, I got a dumb question. Why is that XORing done?
So it's just XORing. I do not know. I mean, their implementation. In the implementation, what they did is like it may be possible to guess this location or the cookie itself. But if because the value of EBP is continuously changing, so attacker may not be able to predict the value of EBP. So we are just XORing this value so that the attacker may not be able to guess this or some sort of this kind of stuff.
This one more confusion.
Yeah.
Like the idea is like when we come back after the execution of our malicious code, we have to check for that security value that was presented there by the function, right?
Yeah, but not the malicious code. We are not executing right here the malicious code. We are executing the normal function. But in the previous case, when we return without removing these checks, we are returning blindly onto this address, which address was overwritten. In this case as well, it's overwritten, and we are just landing onto our payload. But right now, it is checking this position, and before returning, it is checking this thing. And when it is checking this thing, because we overwrite this thing, then we cannot say that this value is equivalent to the ECX register. Then it will jump to this thing, report JS failure. Now we have to look the report JS failure, what this is doing. That I have a snapshot just in a bit. That it will just terminate the application when we use.
Is there not a possibility that that random 32-bit number that has been put there, it can be stored in some other location and...
But the main thing is that before executing your own code, you cannot do anything. Right? So you must have some control over something so that you can store this value to something. But you have no control rather than just overwriting this thing. You get control here, but it is killing right now, right? So So it means it is definitely, from the looking, if we look into this, then this is definitely a killer method. We can say that it will definitely remove all the problems and the buffer overflow. And it is. I am not saying that it's something garbage, but it is a truly a remarkable work when we look into this thing. But it has some problem as well, as we discussed in the previous section, how the cell work actually, the override works in that case. So it has some fundamental problem as well. So, and that problem turns into the bypassing, and we call them as a bypassing technique because we are using them. Now, let me to revise the thing that previously that we used in this override, the recap thing. So in the recap thing, what we did is we overflowed this buffer up to this point, and we used here our own pointer to pop up right, and then a jump to here or here, the forward or backward jump, right? Now, the thing is, an exception handler can only be called when we have an exception in anything. So, it cannot be, I mean, here I can imagine my control here, because the function is returning itself here. But I cannot imagine my control goes here. So, before I land here, I need some sort of exception so that I got execution here. Got my point? So I am saying that this thing is in my control. Because function return at this address, I remove this part. Because function return at this address, so this thing is in my control, because function return at this address. But in say override, I mentioned that if you override this say, then we are able to execute our code. How? But the idea is because if we override this thing, then we override this ret with a something. This is an invalid instruction or invalid address. When function return to AAA, and this address is invalid, right? So it will generate an exception, and that exception comes to here, and that's why I was able to execute my code here, because I am getting the execution right here. It means, in one way or another way, I am generating an exception. Now, if the JS cookie is all there, so because JS cookie check failure is done, and before it done, then it's terminating the application in that function. So I cannot reach here because it's terminating the exception. Now for the bypassing, because there is no check kind of here, so I have to generate an exception before this check. Because if I can generate the exception before this check, then I can land into this area and I can execute my code here. Got my point? So the idea is to generate the exception before the cookie check. Before we actually check the cookie, we generate the exception. And here, we have two things. One is the code dependent, which is depend on the vulnerability condition or the code or the actual exploit condition, and another that we can control, and sometimes we may not be able to control. By the way, this technique was given by David Lisfield of MGS Secure, I think, and in 2003 he written a paper on this. In the code dependent, it means that we get execution right here. It means before returning to the function itself generating an exception. How is that possible? For example, take an example of a pointer, right? Pointer, something a local pointer, which is a local variable, and the pointer, we have the address of that, and we are storing some value into that address. For example, let's say we have a AAA address, we overflowed this buffer, and this was actually our valid pointer in that function, and we are just storing 6 value over this address. I mean, at the block of AAA, we are storing 6 address. Because A is invalid right now, so it may be possible that it may generate an exception there, and we got this handler. So it is based on the code dependent. I cannot say that this is not universal or nothing is. It entirely depends on the code that is manufactured by the programmer or the compiler at that time. So if it can generate the exception, then it's a win situation for me, and I can go over there and I can execute my code in a traditional way that I was executing. And another thing is basically, if we have the control over some instructions or like a classical buffer overflow, in most of the cases, we can override this long way. We will not end here, we will overwrite it to the end of the stack, wherever is the last address. And when we try to overwrite above that, then it will generate an exception, because that memory may exist or may not exist. And we land direct into here, because this is what we are supposed to be exception handler. And then we again exploit this thing using our traditional method that was like used for the exception handler override. So So now the question question that I asked in the previous slides is that which one is more reliable? So the idea is it doesn't matter you get read, overwrite or say overwrite. If you get both, then it's preferable to go with this thing because it doesn't matter what happens, what type of exception or what type of thing happens. You will land into this area and you execute this thing. So this is the GS cookie bypass, and here is another one thing. These are the two traditional methods that we basically use. But there is another one that what if the attacker is used the security exception handler into that, and this is the report JS failure function, the function or the code chunk that is jumping to. Here we can see exactly that it is calling some sort of exception handler, setting some exception handler if there is any, and then terminating the process right here. So the game will end here. We will not end up to this point. But if there is any exception handler, then it may be possible that it's stored on the stack and we can overwrite that and we can execute that as well. But this is the preferred method when we use the bypass. Now, the thing is are we able, always be able to execute using these techniques? There is like, so it means that this implementation has some weakness, right? And we cannot completely deny these things. So my whole point is that this is a nice thing that is like it was a very good forward step to build the protection scheme, but it had some flaws that we can discuss. But if I remember correctly, then I think in the past a Adobe or Internet Explorer exploit was there that was just not going here and next step, but was returning to this red instruction, and because of this cookie, it was considered to be just a random dose. So, in some cases, it is quite possible that you can block the execution of the application. So it was the GS cookie bypass. Any question? Right.
Can you please go back to the previous slide? If the developer has put a terminate condition after an exception is found out, in that case, how are you going to bypass it? Can you please come that again?
Which one thing? The security exception?
Yeah.
Before calling the actual terminate function, you see that it's calling an handle exception filter. The set and handle exception filter, which is used to set the address of that thing. And you have this function, then again calling this function, which is actually when you handle the exception, this is the function that you call when you handle the exception inside the layer. So now we are able to bypass this thing, and we jumped into this thing. Because we jumped into this thing, so they realized, okay, we have to secure this area as well. Now we are securing this, now we have to secure this area, and the good option for that is to use safe set, which they called is the safe set. Now according to the safe set, is again a compiler and linker option, as I mentioned in the previous slide. What they are doing is that when you compile a module, the compiler will actually create your try and catch. It will fetch how many try and catch you are using into your code, and then fetch those addresses and put into a static list. And which it calls that because it's at the compiling time, it is as a secure list. Or you can say that these exception handlers are safe. I can call these exception handlers at any time. So the idea was whenever you call an exception handler or you execute exception handler, you check with that static list. Because we override, so it means that our address is not into that static list. And that failure becomes, again, terminate the application. So this information, the handler information actually, at the compiling time, it's stored into the load configuration directory. If you remember from our PE tutorial, then we said that in the optional header, we have 16 directories, including IAT, exportable and everything. Then there is also a load configuration directory where you store the meta information of these things, these addresses, and the loader at the runtime will actually translate these addresses and make a list of them. But there is an interesting thing of that, because it's a compiler option. That interesting thing is actually, when you do not compile the module with the safe set, then there is no check, because it does not have the list for that module. And it has to call whatever is given to that. And this is a very, very nice point here that we are making, that no check is done to ensure the integrity of the handler for that module. And this basically turns out to be the bypassing thing. Because it is possible that a module or a executable is using multiple libraries, multiple DLLs and multiple type of things. And those DLL, because compiled by the programmer, it is possible that even the main component, it is possible, is not compiled with the safe set. And if those things are not compiled with the safe set, it means that we can use the pop-up ret errors, whatever our sequential thing was there, then we can use that thing and we can execute our payload. So that is the one thing that we can do. But there is a thing, like, what if we have all the things or all the loaded binaries is compiled with the safe set? Then we end up with it. Then again, the great man David Lichfield did some research and identified this thing. Said that use the address that is outside the address range of loading modules. What does it mean? Is basically it does not have the static list for those modules or whatever is outside the safe boundary. It does not have the list or the list of the exception handler. So it means if you use those addresses, then you can the pop-up return address from those modules, then you can actually execute your payload. Now this term here, the outside the address range of loaded module, is something very tricky to understand that what I am saying actually is the outside the loading module. So I will show you the example of this actually. So these are the loaded modules. The loaded modules means the loaded libraries that I am saying. Right? These things are loaded into this. Now, these things, assume that all these things are compiled with the safe set. So we have no option. We cannot use any address from this location because the loader have the static list of these modules. Now, if you look into the memory side of it, then we can say that it starts here, this address, we do not know, this may be the garbage, may not have the valid instruction, whatever we have to search those things. But these are the components that are the loaded components, right? And if you look a little bit above, then we see something like this. Which are not mentioned anywhere in the loaded modules. So the idea is to use any address from these locations. If you go to this thing, then if you follow into this assembler, I think. Which one is this? Then down the line you can see some sort of instruction that are actually compiling into the pop-up ret. Actually, if you go into the specific addresses, when you identify the pop-up ret, you can find easily if you search into these locations. You can find the pop-up ret instruction and you can use that thing. But it doesn't matter. Whatever we have is actually we have to deal with that, and it also has some problems into that. If we use the address from that location, then we come up with a very dangerous thing again, and that dangerous thing is because of this 0 IP. This 0, because this 00 in the hexadecimal is basically act as a string terminator. When we use like this address in our shell, then it means we can overwrite up to here, we can not overwrite down to here, because it acts as a string terminator and we cannot call flow after that point. So then again a thing comes which is known as I don't know remember if I got this thing in the last session, but it again comes as a forward and backward jumping. And the idea of the forward jumping in the previously what we are doing, we are jumping right here, like 6 bytes, because 4 bytes this address, and for the safer side we are jumping just the 6 bytes over here, and we are executing our payload. Now idea is to jump here, somewhere here, right here. For example, because this is also our payload, so instead of jumping forward, we will jump to the backward location and we will start executing our payload again. So, but in some situation, depending on the condition, it may be possible that this payload, this space may not be the full space for our cell code execution or payload execution. And if that happens, then we again end up with a DOS kind of stuff. So this is actually covering the safe cell bypass, what you call. If you have any questions, then
Ahmed, I would like to add a few points here about safe SES. Thing is, the point you mentioned about the load configuration directory. See, we have a static list of all the valid addresses to which we could jump through the SEH handler. And once we use an address for pop-up read, once the address is out of that list, the application doesn't actually know whether this particular address jumping to this address is a valid condition or it is invalid. In that case, application will fail open. Now this is fail open security. Once you don't know if it is true or false, you assume that this is true. This is a valid path actually. And in that case, the application would allow the addresses that are out of that static addresses. The static list is a list that should be used, that should be the only list, that should be the only addresses to which our application should jump. But if in case we use an address out of that list, application doesn't know how to behave. In that case, it would fail. So application would actually allow the outside addresses to be used as the next SEH handlers, the addresses for the next SEH handlers.
I don't know. I mean, he just took this thing in different words, and I use this thing in different words because if the address is not in the list, then it's again. I mean, this is a simple thing. If the address is not in the list, then it's again exited. So I'm not covering this part right here. I will jump to a different thing. This is client side exploit. As I mentioned in the zigzag approach, then because I covered a lot of stuff in the previous session here, and it's not very easy to digest that material in just 15 minutes or 20 minutes. So this is a bit of a little cheaper, you can say, regardless of that. So in the client side exploit, when we talk about like client side exploits, if you remember, like from the past, in 2005 or 2006, I think the areas, or 2002, then there were lots of server side of exploits, and people were like hanging around and saying it's a FTP exploit or it's a web server exploit and these days. But right now the trend is different. Now the people are looking for the client side exploits, and the main area is basically it's a solid infection vector. You have many clients out there that are waiting for the infection, and they can turn into an army, and you can use that army to point anything. I mean, you can destroy the Microsoft website, you can destroy Apple website, or you can do whatever you want to do that. And that's why it's the personal choice. And another thing is basically because most of the people are not aware of these security things. Now I know these things, but before I coming to join this type of field, or I started my research into this field, I was not aware of these things. And maybe many times, multiple times, my browser got exploited by some of the exploits, and many times a botnet or virus maybe landed into my system. So it's a solid infection vector. That's why it's a very crucial choice. It's a huge impact because you have the millions of users outside waiting for the infection, and the landscape as well, because the infection vector coverage is very wide. So that's why it is the part of malicious big infrastructure. And then you call it like a spam, DDoS, or botnets. That a botnet is a really fascinating term. You have the army and you can point it to anywhere that you want to. So that's why the client-side exploits are very popular, and they are very, very demanding as well. I think in the last news, a person released his research, and he was saying that the normal cost, the average cost for any exploit that the malicious person want to, or maybe the government agencies want to purchase, is around $75,000 just for a single exploit. So this is the average. And the biggest he mentioned in something millions, 1.5 million or something. So, but there is a thing behind that. When we typically talk about like we exploit these things, then there is a technique used as heap spray, and I will be talking about just this technique. I am not talking about any specific vulnerability or something, because that is a wider area as well, and we cannot cover this into this time space. So the heap spray was actually designed by Skylin. If you remember his name, he is now the researcher in Google. But he designed in 2005 when he found some bug that was not able to execute his code through these things. We do not have any valid data here or anything anywhere in the program, and he was just code stuck. And then he realized that we can control some of the things in the client things, and we can actually execute our code. Now, it's a code execution technique. It's not a vulnerability or class of vulnerability. We just use the vulnerability and we use this technique and then we execute our code. Now, I again want to put some lights on these topics like EIP overwrite and say overwrite. It doesn't matter, it was a buffer overflow, or it was use after free or memory corruption, whatever it was. But we have to get the control of EIP. And that EIP is either possible through EIP overwrite or the say overwrite. So if we use the EIP and say overwrite, we use different kind of things in this because we thought that we can land into our payload, like jump ESP, because we know that our payload is on the stack and we can jump into ESP and we execute our code. Same with the cell. Now what if we do not have this type of things? Now we do not have the control over these things, or maybe we do not have any space landing here. We have control over EIP, just EIP, and we do not have any other control over this area, or maybe on the heap as well. But we want to execute our code because we have a control over the EIP. We want to execute that. Now heap spray provides actually we use the heap spray, and this provides a very simple method for the code execution, which is very simple. And that method is basically the client-side scripting languages. Now, I don't know if you call it fortunately or unfortunately, but the idea is that client-side applications control some of the variables of the client machine, which is one of the most important variables that is allocate and deallocate memory on the client. So in a JavaScript code, you can put the JavaScript code and you can just feed into your Internet Explorer and you can allocate and deallocate memory based on that JavaScript code. It means if you can allocate memory, then you can feed some information into that area as well, right? So you can write your payload into that area. So when you allocate memory, you can just allocate it with your payload. And when you have the EIP override here, just you can mention some of the address, some down here in the entire whatever the allocations you have, and you can just transfer to your execution. So a classical diagram is this. It means we can make invalid memory addresses valid. For example, the EIP is overwritten with something. For example, just consider just a simple case that EIP overwritten with something like 111111 instead of that. Because 111, if this is the address, then we can think that this address is approachable. If we can allocate some decent amount of memory, like let's say 2 MB of memory allocate. If we allocate the 2 MB of memory on the client, then we may be able to reach to that depending on the heap condition out there, right? So the idea is to, for example, this is the, for example, we are opening an Internet Explorer and we have the allocation just from 200 to 300 address right now. And if we put like 400 address into that, then it will say that the address is not valid because it doesn't exist at this time. And using the heap spray or JavaScript, we allocate more memory on the client. And when we say, I want to reach to the 400 or somewhere down in the line, then it will show me that, okay, this memory is allocated and now this thing is valid. So it means that after the allocation, we can make those invalid addresses valid. And this is a very sound point here that we are building. The idea is to allocate these type of chunks into the heap and fill with no plus and cell code. And the cell code is a term which is your payload. Oftentimes I talk about like payload, we are executing our payload. This cell code is actually the payload, right? The no plus cell code is our payload now, and when we are allocating the memory, we are just entering this data into that location as well. And when we go to the EIP or say override, we just point one of the address into that area and we just start executing our code. And generally the idea is to use the NOP region, because we want to execute the cell code. And NOP is like no operation instruction, so we finally land it to our cell code and we start executing our cell code. And EIP and say override can be by any means. Here it's not limited to stack buffer overflow, it can be stack buffer overflow, heap buffer overflow, memory corruption, or use after free. This use after free is a very nice type of vulnerability these days. Now I would like to code the demo of this thing actually. So the vulnerability that I am specifically talking about as a case study is a very old vulnerability of Internet Explorer. It was exposed in I think 2010, and it is known as an IPS vulnerability. The way that I choose this vulnerability is because of some very nice example, because I want to set some nice example here, and keeping the overall demonstration very brief and very simple. But in the real, it's the real life example. It's not like organizing this thing or cooking this stuff my own. But the idea is to use the simplest form and then explain it how the heap spray comes into the part. But there are more complex things where we can use the heap spray that I'm not talking about. You can just check into the case studies of the previous exploits. But if you understand this concept, then I think you are able to grasp those concepts as well. So it is the Internet Explorer, and we just run the Internet Explorer. So what I will do is I will try to access this area. Now it's saying no memory is specified at this address because this address is invalid right now, and we have no memory at this point. But what I will do, I will use a spray. It means I will allocate a large amount of memory on the browser, and I will try to see if I can access that address. And now I can if I converted that address into the valid thing. So allocate memory on the heap and make the invalid address valid. This is the main theme of this entire heap spray concept. That the addresses that are invalid previously now valid now, and those are valid with our payload. So it means that we can execute our payload as well. So let's say we are opening this file and let's see what happens. So we look onto the memory snapshot, and we will see like if we get the allocation on the right way. So if we go down, this is the normal heap allocated when you start the Internet Explorer. But these allocations seems to be very new because there is nothing mapped here and there, and these allocations are very. We can figure out that there is something that this type of memory is allocated because nothing is mapped there, and we have just one tab or just a single instance, and why this is happening. Now we land into this area. It means that we turn this area into our the lighter zone. That we turn this area into valid thing, and we will use this concept to exploit the IPS vulnerability. So let's take a look into the IPS vulnerability. The reason why I took the IPS vulnerability is basically it was a condition where we cannot control anything of this thing, and the return address was overwritten randomly. Even we cannot control the return address with our address. It was just overwritten with randomly because it's a use after free, and it was taking some pointer out there and then overwriting the EIP. But that address fortunately was very low. So the idea was to approach up to that level. So that address was in like 111 type of thing. And in 111 type of thing, it means that if we allocate the enough, if we do a little mathematics on the heap, then we can say that we can approach up to that point. Now I changed from 10 to 9 here. In the heap spray, you mentioned that I changed from 10 to 9, and you will see the impact of that in the for loop if you saw so in the video. Now it's saying that the EIP is overwritten with 4544A794. Now if I allocate a memory, I think I can approach that, but that takes a huge amount of time or huge amount of allocations that may be too noisy, or maybe the client may just kill the Internet Explorer because it's just hanged and it's not doing anything. So that is also not recommendable. As long as you can get some little lower and with lower allocations, then you choose that address. So let's change our thing in the code itself. Let's change this to back to the 10, and let's see what is the impact of that on the EIP. And one thing is that AIP is overwritten with anything. I am not saying anything like this is my payload or this is my load. That's it. So I change this to again to the 10, and let's see what we get in the AIP. This is the crucial part here right now. So we able to the EIP that we are getting after the 10 allocation is something in the range of 11CF 6A 4A, and something I think if I can approach 0A 0A, then 0A, then after A B C D E F, and then finally I go to 1. So it means I am just away, just a little bit of gap. So it means that with enough allocations, although in the heap spray, in the previous heap spray that I sprayed, I have enough allocations that I can reach into this area. But yeah, I will verify it. And so it means that if I can make this address valid, so it means I am already overwriting my EIP with this address. If this address is valid, then it will start executing that address. It's generating exception only because it does not know the continue, because memory at this address is not readable or not available because it's an invalid address. So we will note down this address and we will spray again, and then we will see that if address at that time is available or not. So I will note down this thing in Notepad. I assume that everyone is understanding. I mean, this is not difficult or not a rocket science. This is just we are making the valid memory address just valid address. So let's say again start this application, and let's start this experiment and see what happens. And after, if we can make this available, then what we do is we include this code, this spray code into the IP itself, so that before we first allocate some amount and then we call the IPers code, so that after that it will get we get the EIP that address, and that address is valid now, and we start executing our code. But let's see just with the spray code we can able to make up to this. Now we again look into the memory to see if we have the right allocations on the right way, and we can see like we have the locations. So we'll just use this address, and we will just go to this address to see if it is available. Okay, now this is all done. So the idea is to use this allocation at the first point before the IPers, and then calling the IPers code that was causing the confusion to our application or writing the EIP with that. Because before, when we do the allocations before, then it means we are making this address valid. And when we use the IPers, it means it will land into this address, and this address is valid now. And we start executing nope, and then whatever the cell code right there. Right? So let's make an exploit of this, and we just copy this thing into IPers. So this is the function, and okay, and in that trigger vulnerability function, we just call this function before, so that we get the allocations before and then the vulnerability after that. So yeah, that's all done. So it means we will get the allocation, and then we will land into our area. Mention that our cell code was not here. I am just using CCC, although I mentioned this. because I'm not using any shell code. But you can paste, just cut and paste the shell code and paste it here. It's just to demonstrate the heap spray and what heap spray can do. So, for example, I'm a layman and not that layman, I'm some a bit technical and I know this thing. And I'm just playing, I'm not a professional exploiter or any professional. And I'm just identifying, and I'm fuzzing the application, I identify this bug. And this bug is like in 2010 it was exploitable. And I created a whole, like the Microsoft is not doing this thing or whatever, this, right? So heap spray makes it very easy to actually execute our code, and now we land it into our code. So the heap spray does not require that much of sophistication. Even the sophistication that we used in the, as you mentioned, C, the CC is overwritten there, and we are just executing this CC right here. This is our execution point right now, currently the EIB. So it means that we can execute and a normal attacker actually can execute. I mean, it does not require that much of sophistication. You know, if you look into the like normal buffer overflow that we use, sometimes that may be tricky in some situation. But here, we are exploiting Internet Explorer 7. There is nothing like I'm taking an application that is a demo version or something like somewhere. This is the real Internet Explorer that is used by the thousands and millions of people. So this was the heap spray, and the heap spray is the stability comments there comes, because the things are not as simple as I shown. Because this is a special case, as I said that I picked this just to demonstrate this thing and keeping it live and impactful thing. But it's not just like I'm saying that I'm using some gas. If I can approach 0A, then somewhere I can also approach 111. And I was saying that 4, 5 will take lots more of locations. So it was something that I'm doing some mathematics on my mind, and I'm saying that this is something that I can get. So this is some sort of intelligent guess. I would say that you have to use some sort of guessing around there. When you have the vulnerability and you have exploitability conditions, then you have to guess around here and there, and you have to identify like, okay, what this thing is feasible. Because you are doing this thing on the client machine, and the client machine if just hangs out or something, then he just click away and we are gone. But in the normal and professional exploits, we never want, and we always want a reliable exploit. And this is a full ground industry, and you have the core impact of the most powerful exploitation and immunity and outage. Stability depends on the exploitable conditions, as I said, but it's found to be very reliable condition. As almost you see Adobe, I think the Adobe Internet Explorer or something that supports the JavaScript or VB scripts, something kind of that stuff. The people use just heap spray. Even you can say the directed attack that we have seen so far, like in the Adobe or the exploit that was sent to specific people, or that comes into in some private way, and that are also using the heap spray because it's so common, and we make the exploit so. So the fragmented heap, if you have a fragment, what is the meaning of fragmented heap? Just note down, because it's a large term. It's basically when you using like, let's say the Internet Explorer, and you are opening 10 to 20 tabs, and your Internet Explorer is running for let's say 1 hour and 2 hours. Then it may have allocated and deallocated lots of memory chunks, and then you may not see the sequence of these things. So somewhere allocation, somewhere deallocation, somewhere allocation. So it means that you use a little higher address before that, so that you do not land into somewhere into that. But there is also, if you use the large number of allocations, then you have to choose a little lower address, and this is contradictory. So you have to make the intelligent thing. So I will come back to the DAP. Okay. So any question here? Okay. So the DEP is a little bit complicated subject. Now the DEP is of two types, software DEP and hardware DEP. But we will be talking about the hardware DEP because software DEP is just because you can say the safe set type of thing. It's just use the SAP protection. And hardware DEP is basically in a rough way you can say that we cannot execute from non-executable area anymore. The stack is a non-executable area. The allocations that in the heap spray that we used are not executable. They were the read write. They were not executable permission of that. and we were executing previously. But now with the hardware DEP, it means we cannot execute that. We cannot just simply heap spray that thing, and we cannot execute our code because that memory location is not executable. And we are dealing with the processor because we are talking about the hardware, and that is permanent DEP. I am not talking about opt-in, opt-out, or whatever the method they are using. But the permanent DEP, it means you cannot go away around this thing. You have to find out a solution if you want to make an exploit. And that the thing that they identified actually, it was not, it's not a rocket science or nothing like return-oriented programming. I think that this thing was explained by some hardware hacker that he mentioned the return-oriented programming. But it's nothing. It's just like return to libc that we use, and it's just like a normal, just the advanced version of that. The idea is the same. We use the system for the existing code here. We will not, like in the cell code, we will use the cell code here as well. But in the cell code, we manufacture that code our own, and we try to execute that code. But in this thing, we will use some of the system code, and then we will land up to our cell code so that we can execute our cell code. Now the idea comes here is return-oriented programming. As the name states, that we have to use some sort of return instruction out there. So whenever we use in return. Whenever we use the return. And it comes into how stack works. And the thing is very simple. When you go to the function just, you pick the return address, and then, so if you use a ret instruction, it simply means that whatever on the current ESP is, just pick that and then go onto that location. This is the normal functioning of return instruction, right? And in the stack, there is two operations like push and pop that can increment and decrement the stack pointer. I mean, if you do not know this concept, then it's very hard to understand this material. But the thing is, when you use push and pop, then you can increment and decrement the stack pointer. And when you use the return instruction, then it means that whatever the current location of ESP, just put that address into the EAP and start execution of that. And we will take the same example of this, because the system and existing code have the ability of execution. They have, because it is the code right now. So for example, it's into the user 32DL or kernel 32DL code. But that has the executable because it was supposed to be executed by the application. So we use some small things of that code, and then we will manufacture a kind of thing, and then we will finally land into our area or our server. Now, before I go into that, I am not covering the stack pivoting into the demo itself, but it is very interesting here. The idea I made here is to, depending on the conditions, it may be possible that we do not have the space on the stack. But as I said, in the return-oriented programming, you need stack. You need stack operations because you are using the ret instruction. You need that part. I mean, you need the stack working out there. And on the heap, you cannot do that. So it means you have to change the EAP in such a way that you can convert the heap into stack. So it means that flip the heap onto the stack so that we can get the larger room, or you can say that we can get more flexibility on the thing, so that whatever the size of the payload we have. Like for example, in heap spray, we can use any amount of the payload because we have so many of locations and so many of space. So the instruction like exchange ESP, reg ESP can be used. So for example, exchange ESP EAX. So if I have a location, I have an address in the EAX, I can change it with the ESP, and then ESP point to that location that the EAX was. And then we are turning the stack, and then we can put our payload onto the EAX location, and we can return it to that area. So we can also jump into the valid instruction. So it is this instruction actually, if we jump one byte inside this setgal instruction, then we can convert this instruction into exchange ESP something, EX or EDX, some sort of. And this is from the live exploit, and which was exploited by, like in the wired, it was Adobe U3D exploit. And we discovered it in the analysis of Adobe U3.
So how are we going to change the meaning of the instruction after we jump into an existing instruction?
Because the thing is, any processor works on the opcode. So if you can change the opcode, it will change the instruction.
But
so for example, let's say if an instruction, let's say a call instruction is going to E8, some 8990, something like that. E8 stands for the call instruction, so it will assemble into the call. But if you land into the A9, then A9 maybe means jump. So it will change the instruction to the jump because it will pick another memory and then convert the link, the instruction in that way. Got my point?
You're going to make changes in the op table itself, in the op tab itself.
No, I am not changing into the op table, but the meaning is that whenever the processor identify E8, it means it is
Means it has got a certain
call.
meaning.
But when you say 8, 9, it will change it to the jump. It will consider it as a jump. Just that simple. We are not changing it. The jump inside. Oh, sorry. You are taking that. I am jumping into the instruction.
Yeah.
The jumping inside the instruction means I am jumping one address inside that. Because these things are one byte instruction. This is a 1, 2, 3. If I go to the one address, then I go to the 2, then it's a jump.
Second byte.
So these are the methods. Actually, I forgot. Yeah. Actually, there is the main theme. The theme was to because we cannot execute from the non-executable area. So the theme is to either create non-executable area executable, else allocate new area with executable permission. So heap spray, we are using heap spray. Then we have to use some sort of logic inside that. Even we cannot execute with the heap spray, we cannot allocate executable area, but we have to use some sort of like heap alloc, the API, heap create, virtual alloc, and virtual protect basically change the permission of the thing, and virtual alloc and heap create basically give me the executable permission if I want allocate the new area. And oftentimes the small code chunks in the are termed as like gadgets. We call them gadgets. These small code, the small return instructions. So some of my things may not make sense right now, but let's see if this makes sense. So we have an application that is vulnerable. Now I am just showing here the DEP bypassing, but the application is not enforcing any kind of DEP. I am just saying that I am executing my code through the system code. I am not executing it's on the stack or something there. Right? So this is the thing. This is the vulnerable application. You can download, and I can give you this exploit code. And if you see in the after the shell code, then generally we overwrite after this with the jump PSP instruction or something like that. But you see something different on that payload area. And if you look into the write process memory it means from one location, the payload from the one location, overwrite the payload into the another location, matching its constraint whatever they have. We have the right permission on that and this and that. So this takes 4 arguments. Now, our idea is to prepare something for it, so that when we call write process address, we have the right parameters on this stack. So before we call any function, we push the argument to that function on the stack. Right? So idea is to prepare the stack in such a way that we can finally, when we execute the write process memory, we will finally execute our code. So this actually is I'm making this thing actually to prepare this stack, because I know. And if you remember, I am using just for the simplicity, I am using just one instruction. There is no restriction on these gadgets. As long as it fulfills your requirement, you can choose any type of code. But I am choosing just for the simplicity. I am using like pop ret and pop EBP ret, and I am preparing my register, and finally I will prepare my stack. So and I will put my exploit into this thing. Then I will land onto the, instead of like using jump PSP or something like that, I will land into the copy AX. And my payload, instead of like in the previous example, what I do, what I have did is like I have written this thing. I have overwritten this thing with my payload, and then I used this thing with the jump PSP so that I land here, I will execute this thing. But right now I am not doing that. I am using these pop ret gadgets, and then finally I will add something here, and then finally I will create my stack frame for write process memory. So let's see how this thing goes. So this is the pop EAX we have, and it means that whatever on the stack, we will just pop that address, this address, into, and we have our payload as well, that 4141 that we overflowed with, right? And in the pop EAX means that we will use this put this address into the EAX because it is the pop. It's pop, whatever on the current stack, and we can see the EAX is now that address that was on the stack. Now we land into the, because we use the ret, it means we land into the pop EDA ret. So the pop EDA ret. Now pop EDA ret, what will do, it will put the the address of the current thing, this thing, call EAX address into the EDI. Because pop just use the 4 byte, put into the register, go to the next thing. Now it's a red. Now if I use red, then I just land into the pop ESI red thing. In the pop ESI red, I will just put the FFF into the ESI and then land into the other gadget. And then I used into the pop, I landed in the pop EVP. In pop EVP, I will patch this address. This is a patch. I will explain what this address is and what this address actually signifies here. And in the pop EBX, I just use the whatever the next instruction, the FFF. I will put the FFF into the EBX and then land into the another instruction that is in EBX red, because that is the normal red functionality. So let's see. Okay, so we are landing into EBX. Now, just for the simplicity, I am using just one instruction in EBX red, just for the simplicity. I could have used one of the advanced gadget here that will change the EBX to my desired location, but instead of that, I am using in EBX with 300 times. It means I am implementing the EBX with 300 times so that I can get the payload or something like, some sort of logic here is there. But I could have used like move EBX 350 is there any into the existing code, and or some other similar instruction. So I will execute this thing and then I will end up to the push address. The next because this is the next address that we will after the returning thing we will end up to this. And if we just a bit, that it means after the red, I will go to this location, this address, and this is the push right? This is the next address, the push what? The push instruction basically put the content of the register onto the stack in reverse order. So first you have the EDI, then you have ESI, EDP, ESP, and then. So your 8 registers are now on the stack. So you will see actually, like, I don't know if you are understanding it. Actually, I am building a concept here. I am putting the parameter of write process memory into the EX register into such a way that when I use the push instruction on the stack, I will get all those parameters right into the write process memory. Right? So this patch, I am saying that why I am saying this patch is basically I am using my payload. As I said, in the write process memory, I write my memory from this location to this location. So the next location should be my execution point, because I want to execute my code. Now here here is my payload that I cannot execute because of the non-executable permissions. Now the next address should be the executable, and that is the patch. And that patch is basically the code, the next address of the write process memory inside the system. Because the idea is, whenever you finish the write process memory, you will land up to the next instruction, and the next instruction is write process memory itself overwritten that thing with my payload, and I will land just directly into that location. So this is the actually the way down the anti-write process virtual memory that will actually write the thing. So what I am doing is, whatever my payload is at this location, from this location, overwrite the thing to this location. So whenever I finish this code, I will finally go to, because the red instruction is red address is this, I finally got my execution there, and I will able to execute my code. Because this is executable, and this is not like this is a valid code. This is the executable area, and we are able to execute our code. So let's see if we can make this. So in the row, the idea is always be like that. I am showing you the write process memory, but you can check the instruction like the another API like virtual product. You can check their arguments, and then you manufacture your things in such a way that you can call the virtual product, and then you after that you transfer your execution to that one. So this is the overall goal of the thing. But once you just it's not that I'm saying that it's not that difficult, but it's a little bit of requires some efforts from the expert. But again, when we talk about like now I'm using the call EX because I prepared this tag in such a way that that whenever I get, because I used POP EDI before, and the EDI is the lowest register. When you use like push add, then EDI comes at the ESP, right on the ESP. And when I used return, push add return, I am returning into the EX register because I prepared the register in such a way. And when I am returning into this address, it means it's calling write process memory. Because the EX register was storing the address of write process memory during my row chain. So I am calling the write process memory with these valid parameters. As you can see, H process means current process address, the next address buffer from what buffer, bytes to write, that 1 to B, that EDX that I increased, and then finally I will land into this. This was a breakpoint actually, and I will finally land into this. So we will overwrite this thing. Once we execute this area, then we will see that this thing is overwritten, and then we have the value. So we able to execute actually our code. And if you see that this location is not, this code is not similar code as the previous it was. And we have some knob instruction there, it was not in the beginning. And we are able to execute our code actually from this side. Next is just, I'm just, before, I mean, without debugger, I'm just checking that it's what it is, and it's what great. And things are not done, sorry, please don't make it.
No, this itself was awesome. Really. Good stuff.
Yeah, and this is the ASLR. Now, I have discussed many things, but this is the bigger thing of all the things. Now, sorry, I'm sorry, but this is the bigger thing, and I'm not covering into that depth into that because I know the sophistication, right? So the address space layout randomization was exposed by some researcher. They were academic, I think it was an academic paper on the PAX project, and they were saying that we can mitigate this kind of thing. The idea was to actually every time when you turn up your operating system, it will do some mathematics on its own and reposition your binary. Now in the current state, if you go to the Windows XP, it doesn't matter whatever you do, you will see the NTTL library or the kernel 32 library or whatever it is, user 32 library are loaded on the same address. We can go to the same address. That's why we use the jump PSP instruction. We use the jump PSP address from like let's say user 32 and we are able to execute on some other location, some other system. Why? Because that was static throughout the operating system. Now in this case, it's randomly. It's something different on my system, something different on your system. And how if you use the jump PSP instruction, then we can execute it, right? And it's a compiler.
Plus, I assume that it will be random even across reboots.
Yeah, it's across every reboot. It will do some mathematics, like it's some entropy checks and everything. Then it will calculate the base, and then it will. It's the option of the compiler right now. It's a dynamic base option. If you compile the library with dynamic base, then loader will do its own stuff. And ASLR bypass is basically search for the non-ASLR logic. Because it's again a compiler or linker option, it is possible that a programmer may have assembled its executable without that switch. Because that switch is not enabled by default because of the legacy application support or something that may using static pointer, because in Windows XP if you see the MSVCRT DLL itself using some static pointer out there. So it will fail in that because the pointer is not static anymore. So in that case you can search for the vulnerable or if possible not one. So as when we talk about like client-side exploit, it is like JRE, Java, it supports some of the libraries that are not not ASLR enabled. So you can use like applet or something, A class or some dummy code, so that you can force that library to implement, and then after that you can use your gadget from that, and you can execute your code. But there are more advanced things you may not be able to. But the memory leaks, like if you have some pointer exposure or somewhere, something like. So it is just assume that if anywhere in my payload that I can control, is there something, some address that can expose the base address of that module that I'm currently in, then I think I can make that. So it's just a simple meaning. And brute force is typically for the server side of thing, that I send my payload and I try to actually guess that what is the base address of this module. And it is possible only because if your service can restart, I mean, automatically. If it's go down, then you just have one switch. But in the brute force, you need multiple shots. And it heavily depends on the vulnerability condition as well. The type of vulnerability, like user free or whatever the vulnerability we have. Then it depends on heavily on those things as well. But in the practice, it's found that if something is like exploitable, then in one way or in another way, we are able to execute the code. So this was like, and but ASLR and D are like very powerful mechanism, I would say. And then there is another like SAO that is again a remarkable word for like the safe side can be bypassed, but the SAO can be bypassed. But using ASLR, D, it saves the SAO. It's a very, I mean, it's raising the bar of the exploit development. It's very high standards. And now we have coming like forced ASLR, in which we may not be able to like. That thing is still coming and the research is still going on. And in the later part, we may be able to, but this is right that we have seen like in 99 or 2005 kind of exploit that, I mean the kids can exploit those things with little bit of yours. But now it's not possible. And that's why the bar and the price of the exploits is increasing very high. Thank you. If you have any questions.